Hello, thank you for watching this video. So in this video we're doing question 9 of November 2022 question by mathematics paper 2. And the topic is Euclidean geometry, as you can see over here. So they are saying, in the diagram, O is the center of a circle. OD bisects chord AB. So we have a circle here, as you can see, and O is the center of the circle, right? AB is a chord to the circle. So a chord is a line segment that joins 2 points of the circumference of a circle. And a chord that passes through the center is called a diameter. So they are saying OD bisects chord AB. What does that mean? It means that your OD, the line segment OD, joins AB at the center, which means it's at the midpoint of AB, which means angle D. So the point D is exactly halfway on AB. Right? If you're saying OD bisects AB, which means OD intersects AB at the midpoint. So this is the midpoint of your chord AB. That's what it means. No problem. Okay, so now what are they saying? They are saying, prove the theorem which states that the line from the center of a circle that bisects a chord is perpendicular to a chord. So they are saying, prove a theorem that states that a line from the center of a circle to the midpoint of a chord is perpendicular to a chord. So that bisect the chord means this line from the center goes to the midpoint of the chord. Prove that a line from center to midpoint of a chord is perpendicular to the chord. That's what they wanted to prove, which means your OD is perpendicular to AB. So this is what they wanted to prove. A line from the center of a circle to a midpoint of a chord is perpendicular to a chord, which means when you say a line from center bisecting the chord is perpendicular, it's the same thing, which means that bisects means the line OD meets AB at its midpoint D. So D is halfway between AD and DB. No problem. So we need to show that OD is perpendicular to AB, which is this line is perpendicular to that one. So if we say this OD is perpendicular to AB, which means this angle here is 90 degrees. That's your claim. Or maybe you're saying this one is 90 degrees. It doesn't matter. You can show that this is 90 or that is 90. It doesn't matter which one you show, as long as you show that there's 90. Because if there's 90 here, there's 90 there as well. If there's 90 here, there's 90 there as well. So that's what they want us to prove. So let's go. Say proof. Right? Under our proof, we'll have a construction, right? Construction. So what are we going to do? We're going to join OA and OB. So let's join OA from the center to point A on the circumference, from center to point B on the circumference. So the length from center of a circle to the circumference is called the radius. So OA is a radius and OB is a radius, right? No problem. Now what we're going to do, we're going to prove that these two triangles are identical, which is they're congruent. If we prove that these are identical, which means the corresponding angles are going to be identical as well. That's what we'll be proving. So that's what we're going to try to prove here. So how do we go about this? Which triangles do you want to prove? This triangle and this triangle. So if you're saying they are congruent, which means you are saying they are identical. In that case, maybe you're saying this angle is the same as that one. Or maybe this one is the same as this one. It doesn't matter, or it matters, actually. So you need to be clear which angles are you talking about. Are you saying this angle is this one is this one, or this one is that one? Are you saying this one is this one is this one, or this one is that one? So the order in which you write the letters of your triangle is important. So for example, I'll say, in triangle, if I say triangle ODA, in triangle ODA, I started at O here, I came to D, I'm going to A. So this is this triangle. If I look at this triangle, the corresponding parts, this angle is this one, which is this angle here is this one. This angle here is this one. and this angle here is that one. So which means the way in which I name this triangle, I should follow the same order. I started here to this one to that one, which is here. I have to start here to this one to that one, which means it will be O in triangle and triangle ODB. Look, if I'm trying to prove that this triangle is the same as this one, I'm saying this angle is this one is this, and this is that, which is evidently true from what I've written there, or from the drawing. So let's prove that these two triangles are congruent. So you know we have 4 criteria that you use to prove that triangles are congruent. I did teach congruence. Go to my bad actions if you are unclear. Right? Fine. So in triangle ODA and triangle ODB, I can say OA is equal to OB, which is OA of my first triangle is equal to OB of the second triangle. So I'll say my OA is equal to my OB. So I'm saying this side is equal to that side. Why? Because these are radii. These are radiuses. Right? No problem. And I'm going to say now, my AD for this triangle is equal to DB of this triangle, because I was told that these two things are equal. Because if you're saying your OD bisects AB, which means D is the midpoint, right? Which is this length is equal to that length, which means your AD is equal to what? Equal to BD. Why? We're given this information. We're told this. Then your OD for this triangle is equal to OD for this triangle, because it's the same side, which is they're sharing. It's a common side. It's common in both triangles. So they're sharing this side. So you're going to say your OD for this triangle is equal to OD for the second triangle. Why? Because this is a common side, which is these two triangles are sharing this side. Therefore, if 3 triangles have exactly equal 3 sides, those 2 triangles are identical. And so will be their angles. So we'll say, therefore, triangle ODA is congruent to triangle ODB, which is they're identical. What criteria? They're identical by their sides. All their sides are equal, which means side, side, side. All the corresponding sides are equal, which means OD is equal to OB. Sorry, OD is equal to OD, OA is equal to OB, and AD is equal to DB. So the same. So in that case, your angle O is equal to angle O, your angle D is equal to angle D, and your angle this is equal to your angle A is equal to angle A. So your angle A is equal to angle B. So in that case, if maybe I'm saying this is maybe just to make things easy, let's say this is D1 and this is D2. Nah? So I'm going to say, okay, my angle D1 and D2 are equal because it's the same angle. Because look, angle O is equal to O, D is equal to D, A is equal to B. So I'm saying O is equal to O, D is equal to D, and A is equal to B. That's what I'm saying. So my angle D1 is equal to angle D2. Why? Because those are the same angles of identical triangles. So those are corresponding sides of congruent triangles. So I'm going to say, okay, my D1 is equal to my angle D2. Why? These are corresponding angles of congruent triangles, which is, these are identical angles of congruent triangles. In that case, what do we say? We'll say, okay, if we add D1 and D2, look at D1 and D2, they will add up to 180 degrees because these are angles on a straight line. You know, angles on a straight line, they add up to 180 degrees. So we say D1 plus D2, angle D2 is equal to 180 degrees. Why? These are angles on a straight line, which add up to 180 degrees. But D1 and D2 are equal. So which means in the place of D2, I can put D1 on the place of D1, I can put D2. So what I'll have, I'll say D1 plus angle D2. But D2 is equal to D1, so we'll just say another D1 here, equal to 180 degrees. Therefore, 2 angle D1s is equal to 180 degrees. Divide by 2, divide by 2. You get that your angle D1 is equal to 90 degrees, which is, we have proven that this angle is equal to 90 degrees. And so is that one, because these two angles are equal anyway. So once you have done that, you want to show that this angle is 90 degrees, which is OD is perpendicular to AB. So we can say therefore, your OD is perpendicular to AB. Why? Angle between lines is 90 degrees. Stop there. So they're perpendicular. And we're done with 9.1. So I'm going to make more space, clean the board, and we're going to do question 9.2. So let's clean the board and we do 9.2. Okay, so now we're doing 9.2. At 9.2, they're saying, in the diagram, E, B, F, S, and P are points on the circle centered at O. GB is the tangent to the circle at B. FE is produced to meet the tangent at G. OT is drawn such that T is the midpoint of EF. GO and BO are drawn. BS is drawn through T, and PS is parallel to GF. So let's look at this diagram. They're saying E, B, F, S, and P are points on the circle centered at O. E, B, it should be F here. So E, B, F, S, and P are points on the circle. On this circle, they all lie on this circle with center O. O is the center of the circle. GB is the tangent to the circle at B. So we have GB over there, that line GB. That's saying it's a tangent to the circle at B. No problem. They went on to say that FE is produced to meet the tangent at G. So you can see FE, this length here, is extended to meet our tangent GB at point G. They're saying OT is drawn such that T is the midpoint of FE. So OT is drawn, right, such that T is the midpoint of EF or FE. So this is a line from center to midpoint of a chord, which is what we just proved. So which means I'll say these two lines are perpendicular from the theorem that we just proved at 9.1. They went on to say that GO and BO are drawn. So GO from that point to the center. BO is from the circumference to the center. So this is a radius over here. And that is a tangent over there. Okay. So they wanted to say that BS is drawn through T. So you can see BS, here is BS here. And passes through point T over there, which is passes through that midpoint of a chord. No problem. They said PS is parallel to GF. So PS, this line over here, is parallel to that GF over there. Fine. Now, before I even start, there are a few things that are obvious. So, this is a tangent over here. GB is a tangent. So, OB is a radius. OB is a radius. You know that a radius is perpendicular to a tangent. So, that should be 90 degrees over there. No problem. What else can you say? We're told that the line segment EF, this line segment EF is a chord. This is from here to there. It's a chord. We have a line from center of the circle to midpoint of a chord. We just proved that it will be perpendicular, so this should be 90 degrees over here. Right? What else can you say? Okay, I don't see anything standing out. Or stop right there. Okay, so let's go. They are saying, prove giving reasons that OTBG is a cyclic quadrilateral. So they are saying O is O, OTBG, a cyclic quadrilateral. So what does it mean to be a cyclic quadrilateral? Which means there is a circle that joins all these 4 points nicely. There is a circle of a perfect radius that can join all these points, which means you can say there's a circle like this that connects all these points. So how do we prove that? So proving. So if you think about, So proving quadrilateral OTBG is cyclic. Okay, let me just say proving quadrilaterals are cyclic. So let's say you have a quadrilateral like this. So let's call it A, B, C, D, main point E here. Let's say C1 and C2. How do you prove that a quadrilateral is cyclic? We want to prove that A, B, C, D is cyclic quadrilateral. So one, you must show opposite angles are supplementary. That's what you need to do. What does it mean to supplementary? Which is they add up to 180 degrees. So in this case, if you say your A1, your angle A, and you add it to your C1, they should give you 180 degrees. Which is if you add this and this, if they give you 180 degrees, then you have a cyclic quadrilateral. Or you can say angle B and angle D hold 180 degrees. If you can show this or show that, that should be enough. You don't have to show both of them. Showing one is enough. You can show if you have a quadrilateral and show that the opposite angles are supplementary, then you're done. Right? You are done. You are done. No problem. What else can you say? So, point number two, you can show, you must show that an exterior angle of your quadrilateral is equal to what? The interior opposite angle. So, D is opposite B, A is opposite C, right? No problem. So, an exterior angle. What is an exterior angle of a cyclic quadrilateral? What is an exterior angle of a quadrilateral? So, an exterior angle of a quadrilateral is the angle between the extended side of a quadrilateral and the closest other side. So, if you look at this quadrilateral, A, B, C, D, you can see DC is extended to E. So, CE is an extension of DC. So, an exterior angle will be between the extension and the closest other side. So, it will be this angle C2 here. Because it can't be this angle here, because it will be DE and it will be CE and DC, which is it's more like the angle between CD and itself. So, our exterior angle is what? Is C2, is this angle over here. So, if you can show that angle A, or actually exterior angle C2 is called angle A, we have shown that this thing is cyclic, which is there exists a circle that can connect all points on that circle. No problem. A third way requires a slightly different drawing. So let's say you have something like this. G, H, I. So it's G. Let's say you have something like this. Maybe can even make it fancy and say, maybe give it some sides if maybe, but there's no need. Let's say you have a quadrilateral like this. Alright? And I want to prove that quadrilateral G, H, I, J is cyclic. How do we show that this thing is cyclic? Of course, you can apply 1 on this one, but you can't apply 2 because where is the exterior angle? You don't have any exterior angle here. Then, a third way, if you can show that a line segment or 2 points subtends equal angles on the same side, then that quadrilateral is cyclic. For example, look at, if you can show that, you can see your IJ here. If your IJ subtends this angle here, let's say this is G1 and 2, this is 1 and 2. So your IJ here subtends G1 and your IJ subtends H1, H2. Your IJ subtends G1 and your same IJ subtends H2. If you can show that this G1 and the H2 are equal, that would mean that your IJ subtends equal angles on the same side. Therefore, this thing is cyclic. So you must show a line segment, which is a line segment or 2 points subtend equal angles on the same side. So if you can show this, then we will have shown, this is the third way, then we will have shown that this thing is cyclic. So I covered all this on my bed action sessions of Euclidean geometry. I did teach all of these things. So in this case, you can show that if you're saying that, if you're saying to me that OTBG is a cyclic quadrilateral, you can show that the opposite angles are supplementary, which is this angle, which is this entire angle here, and that entire angle, they make 180 degrees, or this angle here and this angle here, they make 180 degrees. The sum of the opposite angle, the sum of these two angles, which is this entire angle here, is 180 degrees, or the sum of these two is 180 degrees. Or show that the exterior angle, look at this angle here. This angle here is an outside angle, because look at BT is extended to S, right? So this is, if you can show that this angle here is equal to that angle over there, you have shown that this thing is cyclic. Or show that there is a line segment on a quadrilateral that subtends two equal angles on the same side. But look now, if you look at your GO, you can see your GO subtends 90 there, and your GO subtends 90 here. So, which is the third condition works, because you have a line segment GO that subtends equal angles on the same side, and those angles are both 90 on both of them. But all the information in green is the information that I added myself. I was not given that information, so I need to reason why did I put that information there to begin with. So I'm going to go to 9.2.1. 9.2.1. I said this angle here was 90 degrees, so I'll say GBO. I'll say angle B, right? So angle B. So angle B is formed by GB and BO. GB and BO, that's angle B. I said it's called 90 degrees, so I said that angle is called 90 degrees because this is a tangent and that is a radius. When I was doing theorem 7, I did mention that a radius is, when I was doing theorem 7 on my bed actions, I did mention that a radius is perpendicular to the tangent. So this is your radius, sorry, this is your tangent, GB, and this is your radius, OB. So they are perpendicular, they make 90 degrees. So therefore, the reason, because our radius, which is OB in this case, perpendicular to a tangent, which is what? Which is GB in this case. Right? No problem. This angle, I'll call it what is it? Okay. I'll call it okay. I'll call it GTO, right? I'll say GTO, right? Is equal to what? Your GTO is the same as ETO, which is angle T, which is the same angle, this angle, and this angle, right? And it's called 90 degrees. Why? The reason it's 90 because you have a line from center to midpoint chord. Therefore, it bisect is perpendicular to a chord. A line from center to midpoint of a chord is perpendicular to a chord. That's the first theorem that we proved at 9.1. So we have a line from center to midpoint of a chord, right? So it should be 90 degrees. So what we've shown that therefore the angle G your angle B is equal to your angle T, and they are both equal to 90 degrees. Therefore, your OTBG is cyclic quadrilateral. Why am I saying this? The reason I'm saying this is because the line GO subtends equal angles on the same side. So this side of the cyclic quadrilateral, it subtends equal angles on the same side. So I'll say my reason for this. The reason for this, I'll say GO subtends equal angles on the same side. That's it. That's it. No problem. We're done with 9.2.1. Let's go to 9.2.2 and we'll be done with this question. What are they saying at 9.2.2? They are saying, show that angle O between GO and OB is equal to S. So they're saying, show the angle O is equal to angle S. That's what they want us to show. Show that angle O is equal to angle S. Where is this O? This O is between GO and OB. Where is GO? GO and OB, which is this angle here. They're saying this angle over here is equal to this angle over here. They want us to show that these two angles are equal. Fine. But if you look at this angle O of yours, it's on this circle, on this green circle, because we proved that OTBG is a cyclic quadrilateral, right? So if it is a cyclic quadrilateral, which is there is a circle that connects all 4 points, fine. But look now, if you're looking at the green circle, you can see that your O is subtended by GB. Your O is subtended by GB, is formed by GB on this circle. The same GB is forming T over here. So, your angle O is called angle T because these are angles in the same segment. They are subtended by the same line, GB. So, GB forms angle O and forms angle T. So, these are angles in the same segment. And look at your T and your S. So, these are corresponding angles because this line is parallel to this one. So, these angles are sitting in the exact same position in relation to the lines or in relation to the parallel lines. So, in that case, we can say this angle is called T because these are angles in the same segment. They are formed by the same chord GB on this green circle. And this angle is called that angle because they're alternate corresponding angles on parallel lines. So what I'll say the angle O is equal to angle TE, right? So this angle T, I'll call it BTG. Right? So this angle is called this angle. We said this is GOB, B, or maybe we can say GT, GTB, just for consistency. Why? These are angles in same segment, which is these are angles subtended by the same chord in simple terms. But look now, this angle here, which is the GTB. So look at GTB is equal to this angle here because these are because you have two parallel lines, right? And they're intersected by a common line. So these angles are sitting in the same position in relation to the parallel lines and the transversal. So in that case, this angle here is equal to angle S. Why? These are corresponding angles on parallel lines because your PS is parallel to GF. So look now, your angle O is called angle T and the same T is called to S. So these two are equal, which is therefore your GOB is called to angle S, which is what we wanted to prove. And I hope this question does make sense to you, as it does to me. And we're done with question 9. So we'll move now to question number 10. Thank you for watching. Cheers.